Okay, let us start, I guess. There's not too many people today, but we'll see. Maybe somebody else comes. So, let me remind you what I've been doing last time. And, last time I was doing generating functions, right? And there was the exponential formula, the permutation version. And today I'd like to use it to count the generating function for these C and K. So C and K is as usual, it's the number of permutations in a SAN with exactly K cycles. And so I want to find so it depends on two parameters, like there's N and K. So I want to find a two-variable generated function. Here is a theorem. Basically today I'm gonna finish the permutations subject, and so today I just want to tell you some cool facts about permutations. So let us denote h of x comma t as this two-variable generating function c of n k times t to the k times x to the n over n factorial. So it's exponential in x and I guess ordinary in t. So then h of x comma t is if you try to guess this, then we already know that these Stirling numbers are sort of nice, but just how nice are these? Here, let me. And the answer is that they are pretty nice. So the generating function is pretty nice. If you try to guess it, then it's probably not clear from the definition what it's going to be, but it's nice. So here's the answer. It's just 1 minus x raised to the power of minus t. So yeah, in other words, you write something very simple like this, and you expand the Taylor series, and you see the Stirling numbers of the first kind. You see permutations with cycles, which is completely sort of puzzling. From if I just told you this fact at the beginning, it would have been very surprising. But right now, to us, it's not surprising. So we can, now that we have the theory, we can find the proof pretty easily. So basically, I'm going to apply the exponential formula. And I'm going to be slightly non-rigorous here. So here's what I'm going to do. I'm going to consider a sequence f of n, which is just equal to, it's equal to 0 for n equals to 0, and it's equal to t for n greater than or equal to 1. Again, the non-rigorous part here is that above here t is treated as a variable. In the formal power series, it has no it has no value. But here I'm substituting it as a complex number. So here we're going to pretend that t is not a variable, but t is, let's say, a complex or a real number. But then everything else is straightforward. So you define, let me denote about h sub t of n, the sum over all permutations of f of the size of the first cycle times etc. times f of the size of the last cycle, right? Where C1 up to Ck are the cycles of W. So this is the same setup as in the exponential generated function. You sum over all permutations, f of the sizes of the cycles. But here, f is not just 0 or 1; it's 0 or t. So then h sub t of n is, you can expand this in terms of the I mean, clearly each term depends only on the number of cycles, right? Because f is a constant, basically. So it is the sum over all k from 0 to n of c of nk times t to the k. T to the k comes from, if there's k cycles, then there is a t to the k. And the number of such permutations is c of n comma k. So so that's, if you look at this formula here, then this is a very nice part, which is already appears in that formula. So let us define, as usual, define the exponential generating function h of, I want to write it down explicitly because it's, again, the tricky part here is that it depends on t. So h of x comma t is the sum over n greater than or equal to 0 of h t of n times x to the n over n factorial. Which, so if you compare it to this guy here, then it's exactly, this is exactly the same as the function in the theorem. So all we have to do is compute it, and we can do it by the exponential formula permutation version. What do we get? We get that h of x comma t is the exponential of something, right? It's the exponential of the sum n greater than or equal to 1 f of n x to the n over n. If you remember, in the last lecture there was no n factorial, just n in the denominator. So okay, let's see what this is. That's the exponential of and f of x, well, sorry, f of n. F of n. And f of n is equal to t. So now we're going to switch from t being a complex number to t being a variable. So it's the exponential of t times the sum over n greater than or equal to 1 x to the n over n, which is the familiar to us series for the logarithm. So this is the exponential of minus t and the logarithm of 1 minus x. There is an extra minus sign because of the logarithm, and now I can compute the exponential. So that's 1 minus x to the power of negative t. Very short proof, very surprising result. Any questions? By the way, please feel free to turn on your videos if you can. Where does the t come from again? So originally it wants to, t to the k represents the number, k is the number of cycles of your permutation. So the idea is that I take f of n to be equal to t, basically, because when I write down a sum like this, if there's k cycles, then I'm gonna get t to the k from each permutation with k cycles. Second to last line. Oh, you mean over here? Yeah, I mean f of n is equal to t, right? So that's the f of n becomes t. Yeah, thanks. Any other questions? Okay, and yeah, that's the nice generating function. Let me also mention something else that's, you're not going to be, well, there may be some problems in the homework about this, but the reason I want to mention the next part is that I just think it's a strange and cool fact. So let me mention pattern avoidance. And the definition is very simple. So let me give an example of a definition of a pattern avoidance. So a permutation W in a sen. So W, I want to write it in one-line notation. W1, W2 up to Wn is called 1, 3, 2 avoiding, for example. If basically the condition is that there is no three numbers in the one-line notation which have the same relative order as 1, 3, 2. So like maybe 5, 9, 5, 9, 7 is an example. 5, 9, 7 would be a violation of the 1, 3, 2 avoidant condition. So formally, if there is no triple 1 less than or equal to I less than j less than k, these are the positions where the violation occurs, such that Wi is the smallest one, Wk is the second smallest one, and Wj is the biggest one out of these three. So yeah, that's the condition. So maybe I should try one. Yeah, maybe. So for example, let me try to give you an example. 4, 2, 6, 1, 3, 5. Is it 1, 3, 2 avoiding or not? Can somebody tell me? Does this mean W is monotone? Well, not quite. If W is, you mean the identity? Oh, no, 263. Yeah, 263, 2 less than 6, and then 3 is between them. So this is not 1, 3, 2 avoiding. So, well, if W is monotone, yeah, 5, 4, 3, 2, 1. Yes, it is 1, 3, 2 avoiding. Okay, let me write it. This is 1, 3, 2 avoiding, and also 1, 2, 3, 4, 5 is also 1, 3, 2 avoiding. Is there any other example? Just how many 1, 3, 2 avoidant permutations are there usually? That's the question I'd like to ask. 2, 3, 4, 5, 1. Oh, interesting. 2, 3, 4, 5, 1. Indeed, there is no 1, 3, 2 pattern here, so it is 1, 3, 2 avoiding. Okay, nice. So there is not just monotone. There is slightly more, or there is much more. Anyways, here's the question. But before I talk about how many are these, and I'm not going to actually prove it, even though for 1, 3, 2 it's pretty easy. Let me mention that you can also define the same similarly. One can define 1 to 3 avoiding, 3 to 1 avoiding, and any other pattern. So any pi avoiding for any permutation pi. So you just pick some short permutation, then you ask that, and that's your forbidden pattern. So you have to have no permutations, no sort of subsequences which are in the same relative position as the numbers in the one-line notation of pi. So yeah, anyways, let me now try to count. So let's say I want to count 1, 3, 2 avoidant permutations. So question is how many 1, 3, 2 avoiding permutations are there? And let's say for n equals to 3, what's the answer for n equals to 3? Five. Okay, thank you. That is correct. All right, so all in S3 except for 1, 3, 2. That's the only, because to violate the pattern, you have to have all 3 indices involved. Okay, now let me try to compute n equals to 4, which is harder, but it is instructive. So can anybody guess the answer, by the way? So while you're 8. Okay, interesting. So you're thinking Fibonacci. That's close, but not quite. All right, let's try. Here are all the 24 permutations of in S4. Let me try to cross out all of them, and you're gonna help me with this because I'm gonna not be able to find all of them probably. So I want to find all occurrences of 1, 3, 2 pattern. So for example, here I have 1, 4, 3. So I cross this out. Maybe I should. Yeah, 1, 3, 2, and 1, 3, 2 here as well. 1, 4, 2, 1, 4, 3. Okay, 2, 4, 3. Yeah, this is getting harder. 1, 4, 2. 1, 3, 2. Any more? There should be a few more. Okay, there's 3, 4, 1. No, that's not true. 2, 4, 3. Yeah. Do we get rid of 2, 4, 3 patterns too? Yeah, right. So 2, 4, 3 is the same relative position as 1, 3, 2. So is there any more, or am I? 2, 4, 3, 1. 2, 4, 3, 1. Okay, 2, 4, 3, 1. Okay, yes, 1, 2, 4, 3 is the bad pattern, and that should be it. So there is. I have crossed out Catalan numbers. Yes. So the answer is that there's 14 permutations. Okay, that was slightly painful, but okay. So far this looks like Catalan numbers, but let's try something else. Let's try. Somebody give me. Oh, we did this in discussion. Oh, all right. Did you? Oh, did you do 1, 3, 2? Oh yeah, let's try some. Give me some other 3-letter permutation. Something that's not 1, 3, 2. Just write down the random permutation. 2, 3, 1. Is 2, 3, 1 the same as 1, 3, 2 but reversed? Yeah, that's going to be also clearly right. 2, 3, 1 is just 1, 3, 2 reversed, so there's going to be the same number as. Yeah, just give me something different than that. Or I can do 2, 3, 1 as well, but it's going to be 3 to 1. Okay, how many 3 to 1 avoiding permutations? Did you do that in the discussion, or 3 to 1? There's also 3, 1, 2. Okay, yeah, let's do 3 to 1. That's nice. So for example, for n equals to 3, the answer is 5 permutations. And what about n equals to 4? So let's see. N equals to 4. So I'm looking for the occurrences of 3 to 1. So 1, 4, 3, 2 is an example. 4, 3 to 1, 4, 3, 1, 4, 3, 1, 4 to 1, 4, 3, 2, 3 to 1, 3 to 1, 3 to 1. 2, 4, 3, 1. Yeah, I think this was easier for me. Is there any more? 1, 3, 4, 2. Well, 1, 3, 4, 2. Which one is it? This one. It's not 3 to 1. There is no 3 decreasing numbers, right? Yeah, anything. Okay. Yeah, there is no more. I have crossed out 10 numbers again. So the answer is again 14. Oops. 14 permutations. Which, yeah, if you probably in the discussion you did the proof as well. The proof is again for 1, 3, 2. It's not too hard, but for 3 to 1, it's probably harder. Anyway, here's a weird fact. So weird, I guess, theorem. The theorem is that for any permutation pi in S3, the number of pi avoiding permutations in Sn is Cn, right? Is the Catalan number. 1 over n plus 1, to n, choose n. And so I'm not going to prove it, and I guess proof is, I'm going to leave it as an exercise, I don't suggest you try. I mean, you can try it, but it is probably hard. Anyways, you can do it case by case. You can, for each of the 6 permutations, you can find some probably combinatorial bijection between the corresponding permutations and the, let's say, dig paths or triangulations or whatever. But there is no uniform proof of this fact that I know. Somehow, is it true that for each pi in the sum, the number of pi1 permutations in the Sn are equal? That is not true. So if you look at permutations in S4, so remark, not true for S4. So there are permutations like 1, 2, 3, 4 it's not going to give you the same number as like 2, 4, 1, 3 or something like this. So this pattern breaks in this is really specific to S3, and I don't know why. I don't think anybody understands this good enough. So there is no, I think all the proofs are case by case. Yeah. At least all the proofs I know. So yeah, that's the last thing I wanted to mention about permutations. So if you have any questions, let me know. Otherwise, I'm just going to start a completely new subject. All right, no questions. Okay, and the new subject is going to be about graphs. Finally, we're gonna do some we're gonna count some graphs. And so there is graphs are a prerequisite for this class, and according to the poll I did in the first lecture, it looks like most people know them quite well. But let me still briefly review all the things I need. There's not going to be much of the graph theory that I'm going to need, but for now, and it's going to be convenient for me to use the following notation. I'm going to denote by bracket n choose k, the set of k element subsets of bracket n. I don't know if I introduced this before, but I'm going to use it without thinking about it. So here's a graph is a very simple thing. Mathematically speaking, a graph is just a pair G V comma E, where V is a set of vertices, V is a set, and E is a subset of V choose 2. So maybe I should instead of bracket n I should write V. What is bracket n? Oh, bracket n is the set of integers 1, 2, all the way up to n. So yeah, and that's usually going to be the set of vertices for me. But in general, it could be any set. And then E is the set of edges. So V is the set of vertices, and E is the set of edges, which just by definition is a set of pairs of vertices. And in particular, this definition includes the notion of a simple graph. So let me draw an example of a graph. Maybe you draw some set of vertices, and then you draw some edges. Some edges between these vertices. So maybe so here's an example of a graph. Maybe that's G, right? So the vertices are the dots, the edges are the lines, and in particular, in general, in graph theory, you would allow maybe edges which connect a vertex to itself, or maybe like multiple edges between two vertices. And I'm usually not going to allow that, and that is already included in this definition that E is a subset of V choose 2. So usually we are going to assume that the graph G is simple, which by definition means G has no multiple edges between the same pair of vertices, and no loops, where a loop is an edges connecting a vertex to itself. So, all right, and now let me mention there is a whole bunch of definitions, which I may or may not use. So there's a walk and a path. A walk in G is any collection. Well, it's a sequence. It's a sequence. E1, E2, etc., Ek of edges such that each Ei and Ei plus 1 share an endpoint. So maybe for this graph, you can start somewhere here, and then you can go along this edge, and you can go here, go here, go here. You can pass through the same vertex as many times as you want. You can also go back around the same edge, something like this. So yeah, maybe I should draw an example of a walk. So this is the key point here is that you can traverse any edge and any vertex as many times as you want. Share an endpoint, share a vertex. Yeah, okay. A vertex, share, yeah, that's better, thank you. Let me write share a vertex. Which is, it has to be a vertex of both of these edges. Yeah. And similarly, so a walk allows you to do all this stuff. A path is a path. Ng is a walk, which goes through every vertex, through any vertex at most once. So a path actually, yeah, maybe a path looks something like this. Oops. You start here, and then you go here, and then you go here, and then maybe you go here, and that's it. You have nowhere to go anymore. All right, and finally, there's also a cycle. A cycle is a path. Well, it's not quite a path, but it's a walk, technically speaking. But it has to have no repeated vertices other than the start and the finish. Path with yeah, let me just write it with start equal to finish. So it is, well, in this case, maybe you start at this vertex, here, and then you go here, here, and here. So it's a cycle actually looks like a cycle, like a Jordan curve, I guess. It has no self-intersections, no self-intersections. Yeah, and finally, yeah, one more definition I need is connected. G is connected if any two vertices are connected, well, can be connected by let's say a walk, or equivalently, well, it's an exercise to prove, but equivalently by a path. So, and that's so far all I'm gonna need. Let me give you a few examples. If you have any questions, let me know. Examples which I'm gonna use frequently, and let me use it also to, even though you may know about graphs, maybe you're not as used to mathematical notation with the set of edges and set of vertices. So let me try to give a few examples which are very popular graphs. The most I guess popular one is the complete graph, which is denoted Kn. So Kn is VE, where V is bracket n and E is bracket n choose 2. So maybe K3 is a triangle, K4 is a square with the two diagonals, K5 is the pentagon with a star inside of it, and etc. So that's one example. Another example is the complete bipartite. Complete. So for Kn you just have n vertices and you connect all pairs by edges. Complete bipartite graph, which is denoted Km, n. So here the vertex set is going to be slightly tricky. So let me denote the vertices by. Well, maybe I should first try to draw an example. So an example is that there is going to be m vertices on the left and n vertices on the right, and then I'm just going to connect each vertex to all vertices on the other side. And that's Kmn. And formally, the vertex set is, let me denote the vertices. Okay. Let me denote the vertices by u1, u2, all the way up to um, v1, v2, all the way up to vn. And that's the vertex set. That union is disjoint. And the edge set is then all pairs of u comma v. Which set is the set of all pairs u comma ui comma vj, where I belongs to bracket m and j belongs to bracket n. Yeah, so these two are going to be pretty interesting to us. We're going to count some things about them. And there is also, these are, yeah, maybe I should draw k to 3. K to 3. 1, 2, 3 vertices. 2 vertices. Well, the other way around. Okay, let's try 3 vertices here. And then I just, as you may remember, K3, K to 3, and K5 are not planar, even though so far I'm not gonna use it. Anyways, there is 2 more examples I have which are very simple. So the path is the vertex set is bracket n, and the edge set is I comma I plus 1, where I goes from 1 to n minus 1. That's the path graph. Wait, k to 3 is planar. Did you mean? Oh, okay. Sorry. Yes. Yeah, k3 Okay, I should try to correct myself. Yeah, thank you. I'm being confused. K3. This guy is not planar. Yeah, thanks. All right, so here's the path, and the other one is a cycle, which is v is the same bracket n, and e is, it has one more. E is 1, 2, 2, 3, all the way up to n minus 1 n. So that would be a path, but then there is an extra n comma 1. It's a cycle which looks like this. And so what's important, I guess, in this notation is that when I draw these curly braces, which means I'm drawing a set, that means the order of the elements in the set doesn't matter. So in other words, the graph is undirected. Now for each edge, there is no, I could have chosen a direction for each edge, but I'm not doing it here. And yeah, that's it. So for examples, and now I'm gonna actually try to talk about something interesting. So any questions so far? Also, let me know if I'm going too fast, or yeah, if I'm going too fast, because I'm assuming some background, but maybe maybe I shouldn't be assuming that. Good. All right, thank you. Yeah, that is nice confirmation. So let me talk about trees. By definition, a tree is a connected graph without cycles. So remember, there should be no kind of closed cycle in your graph, but any two vertices you should be able to connect them by a path. So here's an example of a tree. It's very easy to draw an example of a tree, something like this maybe. And let me, and I'm also going to assume that you have seen this before, but so as a reminder, here are all the different, some of the different characterizations of trees. So position, let's say I'm going to assume that G is connected. E is connected. Then the following conditions are equivalent. The first one is that G is a tree, which means that, so in other words, there is no cycles. Because I'm already assuming G is connected. So the first condition is that there is no cycles. The second one is path uniqueness, which is that for any two vertices x and y, G contains a path from a unique path from x to y. For example, maybe I should take this vertex here, and if this is x and this is y, then there is, not only is there a path, because G is connected, but there is actually a unique path which connects x and y. And you can check that for any two vertices, there's always a unique path. Because if you had x and y, and if you had two different paths, then you would get a cycle. Of course, these two paths could have other common vertices in common, so there is, anyway, the proof of this is not exactly trivial, but I'm not going to give the proof because I'm not actually, well, because I'm assuming you already have seen this before. So the other condition is minimal connected, which is that if you remove any edge from your graph, then it becomes disconnected. Deleting any edge from G makes it disconnected. And finally, there's one more, which is if you're into programming and stuff, that's the easiest way to check that your graph is a tree, which is it's called Euler's formula, which is that the number of vertices should be equal to the number of edges plus 1. So maybe I should count. There is 1, 2, 3, 4, 5, 6, 7, 8. There's 9 vertices, and hopefully there should be 8. 1, 2, 3, 4, 5, 6, 7, 8 edges. Number of edges is 8. So in other words, if you write a program, then there's algorithms, DFS or whatever, which check that your graph is connected. Very, very easy to implement. And once you have checked that G is connected, it is a tree if and only if you just count the vertices and the edges. And if they differ by 1, then it's a tree. And sometimes sometimes this is going to be useful, sometimes this is going to be useful, whatever. These are any questions on this, or do you want me to expand more on this stuff? Yeah. Okay. So. And I guess, so in the next lecture, I'm going to try to count different trees. And maybe I should try even. So the question I'm going to ask is, how many different trees on bracket n are there? And I have to explain what the notion of different. I mean, I'm going to do it rigorously later, but for me, different just means, so different means that you have two trees with E1 is different from the same set of vertices E2 if and only if E1 is not equal to E2. So, in other words, I'm talking about labeled trees. As opposed to, next time I'm going to discuss isomorphic, but just to make sure, today I'm only talking about literally as labeled trees. They should be different. So let's try to count. I have 3 minutes left. So let's say n is equal to 2. If n is equal to 2, there is only one tree. 1 and 2, right, so it's labeled, but still there is only one tree, which looks like this. So one tree. Now let's try n equals to 3. I have 1, 2, 3. So can somebody tell me how many trees are there for n equals to 3? Oh, n minus 1 factorial. That's interesting. So for n equals to 2, you get one tree. That is 2 minus 1 factorial. For n equals to 3, so how many trees do you get for n equals to 3? Are you saying that the answer is 2? Or so maybe I should draw one of them. Here's an example of a tree. 4. Okay, let's see. I can also do this, or I can also do this, or what else can I do something else? Or am I done? One, 2, comma 3. Oh, interesting. So 1, 2, comma 3. That's the. Is this a tree or is it not a tree? I don't think so, because you're not the star graph in n minus 1 factorial. It's not a tree. Okay. Yes. Thank you. This is. Well. This is not connected. So not a tree. And the answer is that there's 3 trees. And okay, 20 seconds left. Yeah, let's not do. I'm gonna continue next time. But you can try to think of this pattern: 1 and then 3, and then the next one is gonna be. another number. So yeah, I'm gonna continue in the pre-recorded lecture. If you have any questions, let me know. If not, I will see you on Wednesday, and have a nice weekend, everybody. Thank you. Bye.